Perlin noise is a type of gradient noise developed by Ken Perlin in 1983 as a result of his frustration with the machine-like look of computer graphics at the time. In 1997, Perlin was awarded an Academy Award for Technical Achievement for discovering the algorithm, the award to Ken Perlin for the development of Perlin noise, a technique used to produce natural-appearing textures on computer-generated surfaces for motion picture visual effects. The development of Perlin noise has allowed computer graphics artists to better represent the complexity of natural phenomena in visual effects for the motion picture industry. Perlin did not apply for any patents on the algorithm, but in 2001 he was granted a patent for the use of 3D plus implementations of simplex noise for texture synthesis. Simplex noise has the same purpose, but uses a simpler space-filling grid. Simplex noise alleviates some of the problems with Perlin's classic noise, among them computational complexity and visually significant directional artifacts. Uses. Perlin noise is a procedural texture primitive, a type of gradient noise used by visual effects artists to increase the appearance of realism in computer graphics. The function has a pseudo-random appearance, yet all of its visual details are the same size. This property allows it to be readily controllable. Multiple scaled copies of Perlin noise can be inserted into mathematical expressions to create a great variety of procedural textures. Synthetic textures using Perlin noise are often used in CGI to make computer-generated visual elements such as fire, smoke, or clouds appear more natural, by imitating the controlled random appearance of textures of nature. It is also frequently used to generate textures when memory is extremely limited, such as in demos, and is increasingly finding use in graphics processing units for real-time graphics in computer games. Development. Perlin noise resulted from the work of Ken Perlin, who developed it at Mathematical Applications Group, Incorporated for Disney's computer-animated sci-fi motion picture Tron. In 1997, he won an Academy Award for Technical Achievement from the Academy of Motion Picture Arts and Sciences for this contribution to CGI. Algorithm detail. Perlin noise is most commonly implemented as a 2, 3 or 4-dimensional function, but can be defined for any number of dimensions. An implementation typically involves 3 steps: grid definition, computation of the dot product between the distance gradient vectors and interpolation between these values. Grid definition define an n-dimensional grid. At each grid coordinate assign a gradient vector of unit length in n dimensions. For a one-dimensional grid each coordinate will be assigned either +1 or -1, for a two-dimensional grid each coordinate will be assigned a random vector on the unit circle, and so forth for higher dimensions. Computation of the random gradients in 1 and 2 dimensions is trivial. For higher dimensions a Monte Carlo approach is proposed in where random Cartesian coordinates are chosen in a unit cube, points falling outside the unit sphere are discarded. The process is continued until the required number of random gradients are obtained. Acquired gradient are then renormalized. In order to negate the expensive process of computing new gradients for each grid coordinate, some implementations use a hash and lookup table for a finite number of pre-computed gradient vectors. The use of a hash also permits the inclusion of a random seed where multiple instances of Perlin noise are required. Dot product equals. The second step in the algorithm is to determine into which grid cell a particular point falls. For each grid node coordinate a distance vector between the particular point and the node coordinate is determined. The dot product between the gradient vector and the distance vector is then computed for each node. For a point in a 2-dimensional grid, this will require the computation of 4 dot products and in 3 dimensions 8 dot products. This leads to the complexity scaling. Interpolation equals. The final step is interpolation between the dot product values computed at each node. Interpolation is performed using a function that has 0 first derivative at both endpoints. A linear function, for endpoints at 0 and 1 with values a0 and a1, would be. Noise functions for use in computer graphics typically produce values in the range, -1.0, 1.0. In order to produce Perlin noise in this range, the interpolated value may need to be scaled by some scaling factor. Pseudocode. The following is pseudocode for a two-dimensional implementation of classical Perlin noise. Function to linearly interpolate between A0 and A1. Weight W should be in the range 0.0, 1.0, function loop, float A0, float A1, float W, return A0 plus WA1. Computes the dot product of the distance and gradient vectors. Function dot grid gradient, int x, int I, float x, float y. Pre-computed gradient vectors at each grid point x, y, extern float gradient, y, x, 2. Compute the distance vector, float dx equals xx. Float dy equals yi. Compute the dot product, return. Compute Perlin noise at coordinates x, y, function Perlin, float x, float y. Determine grid cell coordinates, int xo equals x, x, 1. Int x1 equals xo plus 1. Int yo equals y, y, 1. Int y1 equals yo plus 1. Determine interpolation weights, could also use higher order polynomial S-curve here, float sx equals xxo. Float sy equals yyo. Interpolate between grid point gradients, float no, n1, xo, x1, value. No equals dot grid gradient, xo, yo, x, y. N1 equals dot grid gradient, x1, yo, x, y. Xo equals loop, no, n1, sx. No equals dot grid gradient, xo, y1, x, y. N1 equals dot grid gradient, x1, y1, x, y. X1 equals loop, no, n1, sx. Value equals loop, xo, x1, sy. Return value. Complexity. For each function evaluation, the dot product of the position and gradient vectors must be evaluated at each grid point. For each additional dimension, the number of grid points doubles. Perlin noise therefore scales with complexity for dimensions. Alternatives to Perlin noise producing similar results with improved complexity scaling include simplex noise and open simplex noise. See also, simulation noise. References. External links, Matt Zucker's Perlin Noise Math FAQ, Rob Farber's tutorial demonstrating Perlin noise generation and visualization on CUDA-enabled graphics processors, Jason Bevins' extensive C++ library for generating complex, coherent noise values, French tutorial about implementing improved Perlin noise in C.